So welcome everybody to the second day of the conference. So basically it's already the third day, including the workshops on Monday. So everybody, I think, enjoyed the first days, and we're looking forward to a quite interesting date, and especially the morning session. I think it's one of the highlights, clearly, of the conference, because I'm allowed to chair it, maybe. But I think we have three very interesting speakers. We will start with Luca Benini from ETH Zürich. There he is chair of digital circuits and systems, and he is also a full professor of the University of Bologna, and I guess most of you in the room know him or know at least his work. And I think he will share in his talk his insights of more than 10 years, I think more than 10 years of open source, RISC-V development, and yeah, I think we will learn a lot about his research areas, which are highly efficient parallel computing systems, AI, smart sensing, and so on. So Luca, please.
Good morning, everybody. It's a real pleasure to be here. And so today, I'm going to describe a bit of the experience we had in the last 10 years around developing open source RISC-V platforms with a focus on energy efficient and scalable computing. So we know already that computing is power bound. And this is true from the cloud, where we see now machine learning training workload skyrocketing with a double exponential slope, as shown in this picture, and hitting the bound of the amount of power we can deliver in a full data center for this type of workloads. And to train a GPT-4, we need a number that I have some trouble to say what it is. It to e to the 25. So this is crazy, and what is crazy is that it's increasing very fast, 10x every 2 years. Now, it's not only the cloud, it's the edge too. And at the same time, these larger and larger models that are becoming smarter and smarter are being pulled to the edge by numerous applications where the latency and security issues that you could face when you have everything in the cloud would avoid some of these, prevent some of the applications. So again, this exponential trend is actually pushing the edge there. And there, the power envelope constraints, of course, are much tighter, are in the order of milliwatts. So we need to distill our models, but still the energy efficiency is the key. Now, as we all know, technology, even though Moore's law has been declared as dead many times, is actually keeps going and keeps scaling, actually, with a lot of effort, a lot of super smart things being deployed. So while density is increasing, however, power is not scaling at the same rate. Actually, scaling is much slower. So when we have a rate of 2x computational capability increase needed with a fixed power bound, technology gives us only 10x every 12 years. So it's really doesn't match what we need. So we need to work in order not to burn. And what is actually shown here is that necessity is the mother of invention, I guess. So this shows how people have been very inventive to play with what you can do at the architecture and the hardware on the same technology substrate. And as you can see, we have several order of magnitude of computational capabilities, as well as several order of magnitudes of energy efficiency. And people have been playing this to meet their market constraints, playing with new architectures, with bit width, and so on and so forth. So I'm trying to take a principal look at this Cambrian explosion and try to see what we can play and what RISC-V has to do with it. So the way I want to work through the challenges and the opportunity is starting from the bottom, starting from the processing element, and then moving higher and higher up on the compute hierarchy. And fundamentally, there are two main things where we burn energy: compute and move data, okay? As we'll see, compute is important, but move is getting more and more important. So we need to win on both sides. So let me get started from the processing element where the compute happens. And there, let's see what is the main issue. So there, we have operand memories, registers, level 0 instruction buffers. Here, the capacity of this memory is very small. The latency of these memories is also very small. And this is typically private storage. So here the focus is how you can do the best of this limited capacity of private storage and get your computational units as busy as possible. However, our working sets will never fit into this small memory, and then we have to go to what we call tightly coupled memory, which is on-chip memory. This is a higher density, so higher capability of storage, larger data set, but also higher latency. And it is typically shared among many processing elements. So here we have to deal with the two challenges: tolerating the latency to access this memory and sharing this memory very effectively without minimizing the contention and weighting. But also this memory is not sufficient, so we have to go to the third level, typically off-chip. And here we have the density. Here we can store our working set, but the latency is humongous. And we also have the bandwidth problem to get this data. And the cost to get this data from there, it's super large. And here we have the problem of, again, latency and bandwidth multiplied by a couple of orders of magnitude to deal with. So let's start from the bottom. So here is where RISC-V really shines. And the way we address this problem is try to simplify to the bones what is a processing element. And fundamentally, what is a processing element is some control logic to decode instructions, and then access to the memory and access to the functional units that will actually do the job. And you need to get the functional unit rights, but most important, you need to get these interfaces to instruction memory and data memory right. And the key word there is latency tolerance. What does it mean? It means that this processor must be able to issue multiple requests in the memory without stalling after the first request. Is this out of order? Not necessarily. It means that as long as you can queue up several uses of the memory and use the memory for your operation a bit later, late enough to tolerate the on-chip memory latency, then you can keep your processor busy. And this is the key idea. So we need to have a very simple element that is at the same time latency tolerant and doesn't need to blow up to the complexity of an out-of-order processor. The second keyword is extensible. Domain specialization is the key game, so we want to be able to tune our instruction set. After giving a baseline, you need to tune your instruction set to your workload, to your domain, to get best efficiency. And there is where RISC-V, with its by construction extensibility, makes things really great. So fundamentally, we can see this is like a plethora of different domain-specific in-processor acceleration engines that can be fed thanks to this latency-tolerant memory access in a stream-like way. So where you fundamentally are working on the functional units several cycles later after you have issued the memory request. And RISC-V is perfect for playing this type of games because you can extend your instruction set and you can also work on the microarchitecture freely. So that's what we have been doing. And the key point here is that if you look at your typical, dot product operator, that is the simplest atom of machine learning if you want, then you see that the RISC-V ISA, the baseline RISC-V ISA, would do this, of course, but would do this at a very limited efficiency. In fact, over these 6 instructions, the one that really manipulates the data is the only one. And the others are load and store instructions and branch counter manipulation. That's nothing wrong with the RISC-V. Any RISC processor would do that. So how can we squeeze out from the instruction stream all the other yellow boxes and keep only the green boxes. And that's where we started to scratch our head. And the key idea here is fundamentally to elide from the instruction streams the load and the stores, and fundamentally create streams into your registers, directly into your registers, of the data coming from the memory without having to expressly load and store every cycle. This is what is called stream semantic registers. And the other thing is that since your loop is iterating over and over the same operation, you may want to buffer this operation so that you don't have to refetch this operation multiple times. And that's what we call the floating point repetition. It's basically a level 0 buffer, or the way you want to call it. So fundamentally, the stream semantic register means that you have an address generator that you can pre-program at the entrance of the loop, and it will generate the addresses in the memory. And thanks to our latency-tolerant scoreboard-based mechanism, you can stagger these loads into the memory, load and store into the memory, before the use in your floating point unit will be needed. So the address generator, the stream generation hardware will go ahead, fetch the data, and at the end, your loop gets completely squeezed to the single fmadd instruction. So right now, if you can execute this loop without stalls, you get 100% utilization of your FPU, as opposed to 1/6 utilization of the FPU as in the baseline instruction set. So that's the key idea, playing with the instruction set and also having latency-tolerant cores. In this way, you can stagger the loads and get your data, and if you unroll this dependency, and your goal, your streaming register will allow you to unroll this dependency without making your code larger, you can actually keep your memory, your floating point unit fed. This is actually an example of how you can deeply modify the ISA to get this high performance. But there are also other things that you probably are easier to relate with. For example, special data types. Machine learning is all about narrow data types today. From floating point 32 to floating point 16 to bfloat, large range, and moving to 8. So also this is something for which you need an agile instruction set to be able to adapt to the new data types that are introduced weekly. And this is actually another key issue here, is that you have to play also with expanding operations. Fundamentally means accumulating a very large number of narrow data types into a larger accumulation one, which you can curtail later, you can cut later. And here again, you can do it with a standard instruction set, you can do it with FMA, but you can do it better with special instructions. For example, the dot product instructions allows to ingest the full dot product of the narrow data bit and accumulate it in a larger accumulator, and also playing with all the orderings that are needed to make sure that you minimize the precision loss in doing the accumulated additions. So this is an instruction that doesn't appear in the instruction set. It's very easy to support and gives you a lot of advantages when you work with narrow data types. And here we see that, for example, you get, as expected, if you move from 64-bit to 8-bit data types, you get the speed up and also the energy efficiency that you expect. Actually, the energy efficiency is super linear because, as you know, multiplication is not a linear operation. It has a quadratic complexity inside. So, very good news. What about even more exotic extensions? What about sparse data types? This is a big trend now when our transformers are getting into the billion of elements. You want to sparsify them. So again, here we can play the streaming semantic register game again, but at this time we can extend the stream semantic registers to manage sparse data types, which basically means a couple of arrays, one storing the value, the other storing the non-zero indices in your matrices, and then you can work on these sparse data types very efficiently. Again, this type of extensions require intrusion into microarchitecture and support in the ISA, and you can do this only thanks to a flexible and open ISA like RISC-V. Now, this type of extensions gives you quite impressive this quite impressive speed up and energy efficiency, not only on sparse matrices, which are the core of large-scale machine learning, but also on non-machine learning type of operations. For example, stencils. Stencils can be executed very efficiently with these sparse extensions that I described, and we can achieve on a large number of stencils utilization efficiencies that are similar to the ones that we get on dense structures. So let me now wrap up and move to the next step, which is scaling up. So here is the summary. Minimize control overhead, reduce the von Neumann bottleneck with reduce the number of instructions you have to fetch, hide memory latency, and use a highly expressive, extensible instruction set to tune your ISA to the application domain. This is the game we are actually playing the EPI and the EU pilot projects, where we are working toward high-performance computing using, in Europe using RISC-V. Now, the next step I want to spend a few minutes on is where if you want to scale up. Now you have an array of these PEs, and you want them to share memory. And this is on-chip memory. The latency here is around 10 cycles, so it's an order of magnitude larger than the registers, and so you need to tolerate the latency. But we now have a core that can tolerate the latency of this local memory. So we cluster the cores in blocks that are fundamentally share memory clusters, and the memory is L1 memory, so it's accessible in a few units of latency. Our cores tolerate the latency, and then we have to make sure that they don't conflict with each other. So we have to construct a shareable data memory, which we construct as a multi-bank data memory, and then the game is how you provide access to the banks, to the processors, avoiding contention. So this is a game of an interconnect, very low latency interconnect, on-chip low latency interconnect. And then you have the second problem, which is how you bring the remote data into this local memory, and this we do with smart DMA engines that can pack the data and bring it in blocks and establish a double buffering pattern so that your processor can be busy with a data frame while the DMA is working on the next data frame. So let me just elaborate a bit on these two building blocks which we have been working on. The first one is fundamentally a low-latency logarithmic interconnect with a logarithmic number of stages in the number of initiators and targets. The initiators are the PEs, the targets are the on-chip fast SRAMs. This design can be, it's actually quite tricky to get from the physical domain viewpoint, but you can get to the point that you can connect 16 processors to 32 or memory banks within 2 cycles of latency at a gigahertz speed. So that's great. So we can create these 16 cluster blocks and keep them busy as long as our cores can tolerate a latency of a couple of cycles. But our cores can do it, and they can tolerate more. So that's great. We can keep our cores busy and avoid serialization by multi-banking data structures. Now, the DMA. The DMA is, has to tolerate much larger latencies. So it has to go to a global on-chip bus and to memory. We are talking about hundreds of cycles. So it has to be able to transfer very large data blocks. And this has to be able to do it in a very efficient way. Efficiency for a DMA is 2 points. Latency, so we need to be able to configure the DMA engine in just a handful of clock cycles. Again, instruction extensions in the RISC-V help you creating DMA extensions that will help you configure the DMA in a couple of clock cycles. And then bandwidth. We need to have enough bandwidth in the main memory and enough bandwidth in the L1 to be able to transfer these big data buffers without letting our DMA get in the way. And that's the DMA design that we have done, which actually handles data transfers of 512 bits to 1 kilobit, and then shuffles them into the level 1 memory to keep the processors busy with this double buffering that I described. Now, maybe a question is it 8 or 16 cores in the cluster the best? What is the best number of cores in the cluster? That's a very nice question, so we are working to answer these questions. In an 8-core cluster, we see that most of the energy and the power goes into the access to the L1 memory and the FPU, which means that our architecture remains efficiency even when we scale it to the cluster. Now, what happens if I want to scale this efficient cluster architecture. So the concept is we want to create a mempool. And a mempool is nothing else than this level 1 pool that everybody can access. And we want to push this idea higher and higher in terms of number of processing elements that you can have. Now, the question is, can you create a cluster with, 256 processing elements? So where is the trade-off there? Well, it's good to have a large cluster. Why? Because of Little's law. Little's law basically says that, if you want to tolerate a large latency, you need to have a large buffer. So if you create a large cluster with large memory and a large buffer, then your DMA has time to ingest the data and push it back and completely hide the latency of your memory, of your level 3 memory, that is 100 cycles, without running out of buffering space in the L1. So we want to have a large cluster, but to have a large cluster with a lot of memory, we need a lot of processors to make good utilization of this memory. This memory needs to be used to do a lot of computation. So scaling up is good, but if you scale up, your area will become larger, and then your latency into the L1 memory through the interconnect will become larger. So we found out if we keep this latency below 10 cycles, the cores will be able to absorb it thanks to their latency tolerance. So between 5 and 10 cycles, it's OK. And we found out that we can still clock a cluster with 256 processing elements with 5 cycles of latency to the memories in 1 gigahertz. So basically, we can create a very large mempool and play this game of sizing the cluster larger if we need it to scale up our computational capability. Now, the summary of this is the memory pool allows you to efficient sharing of L1 memory. Synchronization I didn't have time to cover, but you need to be very careful not to waste power there. And data mover plus double buffering is really helpful to completely hide your memory latency. And more core and more memory per cluster, if the cores are latency sensitive, makes sense. Now, let me move to the last part of my presentation where I go to the full system, where now we put the L2 memory into the picture. And by L2 here, I mean off-chip memory. Okay, so now the discussion becomes a bit more complicated because now you have to handle the chip boundary. And as we know, the chip boundary today is a chiplet boundary. And the reason why we moved to chiplets, beside the economical reason of high yield and so on, is that it allows us to get a much larger bandwidth into the memories that are outside, but very close, and also lower latency. So that's the chiplet architecture that we have been working on. You can see on the bottom a large pool of several clusters of processors with a local memory. You can see in the red box in the bottom a 64-bit control processor, could be a moderately superscalar processor, that is going to just do the offload, the control of the rest. And on the top, the other big part is the chip-to-chip link that allows you to connect the chiplets and scale across multiple chiplets, each one which is local HBM memory, to have this fractal architecture that you can scale chiplet by chiplet. And of course, you have all the rest that you need. But the 3 main components I want to focus on now are the global interconnect and the chiplet architecture. So, a couple of slides on this. Now, the global interconnect is finally a network on chip. I was working 20 years ago on network on chip, and I'm very happy to be able to restart this work. And the idea here is this network has to have a huge bandwidth, has to be able to deliver 512 bits of data every cycle at 1 gigahertz. We cannot serialize. This network has to be very wide on the chip. And it has to have make good traffic patterns, not only toward the system memory, but also across the various clusters, so that we don't have to bottleneck the system memory to copy in and copy out everything there, but we can have also cluster-to-cluster data flows. So it's a proper network on chip with a very large bandwidth and very large data width. And of course, this network on chip has to extend with continuity across the dies through the die-to-die link, again, super wide. We are talking about thousands of wires, so that we can move data not only when we move out of the chip, we not only move it to the memory, but we can also move it to the sister chiplets in our architecture. So this opens a lot of interesting design choices, software and hardware, to minimize the bandwidth to the HBM and to help distributing the bandwidth on the chip. Now, this is actually a big trend. This is not our own idea. Many other companies and architectures are doing this. So this is the concrete tape out of the project. This is called the Occamy. And this actually shows, as you can see, the HBM on the side, the die-to-die link on the other side, the compute clusters. Each one of these compute clusters has several tens of processors. And overall, we are talking about several hundreds of processors of the PEs that was described in the previous part of the talk. And thanks to the latency tolerance that has been ingrained in all the level of the memory hierarchy, we can keep utilization as high as in the single cluster, thanks to the latency hiding capability and the very large bandwidth that we have provided to this type of chiplets. So there is hope to scale this architecture beyond the on-chip design. This actually was taped out last year, and this is the interposer, silicon interposer. You can see that we created a minimalistic system, 2 Occamy chiplets, 2 HBMs. The chip-to-chip connection is between the 2 Occamys, and each Occamy will have its own HBM. Of course, you can scale the system much larger, but this is already quite a multi-billion design, multi-billion gate design, and it's actually difficult to handle by a university or a couple of universities. So this is what we have tape out. This is actually the interposer, tape out in October 2022. Now, this whole beast, how much can you do with this whole beast? Well, actually, you can vastly exceed the teraflop if you consider narrow data path, narrow data bit width. You're talking about floating point, not integer operations, but you can also, go around 1 teraflop for this relatively small system. And I have to thanks all the industry partners that supported this work, because even with a large group, it would have been impossible to work on this without a lot of industry help. And this is actually, the artist rendering of the final package, because our partners in Fraunhofer are helping us to package the system. And hopefully, October will measure everything together. Good. What I want to mention is that everything I talked about is open source. So all the microarchitecture, from the processor to the NOC, is all open source, including the chip-to-chip link, as you can see. Maybe you wonder how you program this stuff, okay? A lot of explicit memory transfers and DMA and so on and so forth. And this is actually where, partnership with software partners here, I want to, give a big thank to the team of Thorsten Hoffler in ETH Zürich, who is helping us creating a domain-specific environment where we can actually move from a high-level tensor type of representation or stencil representations and actually generate all these explicit data transfers and all the parallelizations, and also optimize tiling, optimize the size of data transfers. And if you are interested in seeing the first results of this domain-specific flow with a lot of optimization inside, see the Rivets presentation by Ivanov on Thursday, tomorrow. So, to wrap up, the efficient chiplet architecture in perspective. So, multi-cluster, single die scaling, NOC for flexible cluster to cluster, cluster to HBM, cluster to chiplet, to next chiplet, interconnect. It has to be a very wide interconnect. I didn't have time to go into its microarchitecture. There will be occasions in the future, but it's actually a very interesting piece of design. And then this modularity of the chiplet architecture that allows you to scale beyond the single die in these very large packages is actually going to be key. And I have to add to the fact that domain-specific tooling for programming is also essential. Finally, at the system level, do we want to put this into machines? Indeed, we want. The first, let's say, driving case, thanks to the HPC program, is going to be high-performance computing. We already set up a cluster of RISC-V only processors that has commercial host processors. A couple of years ago, it's called Monte Cimone, and the goal of Monte Cimone is not to do high-performance computing, but to step up in the high-performance software infrastructure that you need to be able to deploy applications on these new type of fabrics that I've just described. So Monte Cimone is, software development vehicle, if you want. Now, it is being designed for HPC pipe cleaning, so you can see the form factor, the cooling, the power supply is very similar to what you would have in a HPC supercomputer in the near future. And the way we are working with this, waiting for the silicon of Occamy to come back, is we actually emulate the Occamy on a large FPGA, of course a small part of the Occamy, but we have HBM on this FPGA, we can have multiple clusters and so on. Of course, performance is not going to be on par with the silicon, but we will be able to develop all the offload interfaces, all the drivers, PCI Express, and all the connections that are needed to be able to plug in the silicon onto the machine. And what is coming next is we believe that this is going to be a footprint for scaling up performance, not only for HPC, but also for the next generation automotive designs. So our current project is called Occamy. The next one is going to be called Carfield, and Carfield, the name says it, and this is going to be the next big application domain. And with that, I want to thank you and welcome your questions.
Yeah, thank you very much for this very interesting talk. There is room for 1 or 2 questions. Are there any questions? Nobody stands up. Maybe I have a question concerning. I was a bit concerned when you said all this optimization of latency and prefetching, basically, you're doing about the security, which is my favorite topic. Do you think about that in your architectures?
Yeah, actually, if you mean security in terms of timing channels?
Yes.
Yeah. Okay. We actually have been looking into this problem a lot, but I have to say that currently this explicit memory architecture is not tailored toward the secure operation. Where we have put secure operation is in the host. So the main host, the 64-bit host, is actually has a number of timing channel prevention mechanisms, like even instruction set extensions to cancel timing channels when you move from one tenant to the other. But we haven't dealt with the timing channels in the clusters. I think this is a very open and very good question. I don't know how to answer, but we'll think about it.
It's a difficult one, yeah. There is one question, yeah.
With your chip, are you running a generic OS like Linux on the chip itself, or is it like GPU that has a very specific firmware?
Yeah. Okay. So the host that you have, you saw that this 64-bit host is running Linux. No problem with that. The fabric is running a runtime that is only similar to what you would have in CUDA. So this is not an explicit runtime, an explicit operating system, but is managing all the parallelism, the fork, the join, the synchronization, everything. And this is wrapped into the kernels. So this is, you would call it bare metal in the sense that it doesn't offer the services of an operating system. What is actually very interesting, though, is that the cores that we are running, I mean, they run RISC-V ISA. So in theory, if you had a microkernel, like, FreeRTOS and so on, these cores could also run a microkernel. Currently, we are not doing this because we don't see, we see this as a parallel fabric. But the flexibility of the RISC-V architecture allows you to even have a completely different way to manage this fabric, because the cores can run independent code. It's not like a GPU where you have this single instruction, multiple thread. The cores can run independent code. So I conjecture that could be very flexible, different ways to squeeze work out of this fabric. It is not just blasting kernels into it, because the ISA allows it and the microarchitecture allows it.
I would guess most of the ideas about special instructions, for instance, could also be existing in a generic core that you would use for a server.
Absolutely, absolutely. The reason why I focus on on this fabric is that we have found when looking at the host is that if you want to use, if you want to have the full flexibility of a application core, then you need to support virtualization, you need to support security, you need support true out of order, and so on. And then, the budget of non-FPU stuff around your FPU becomes 10 times larger than your FPU, while in this case, our FPU is 10 times larger than the core. So it's a bit of a different balance.
Okay, so maybe one last question, but then we have to continue. Yes.
As workloads get larger, traversing workloads go ahead and trash your caches, and the sparse workloads thrash your PTEs. Have you addressed any of those things?
Yeah, actually, the idea of the sparsity handling, I haven't talked about. There are hardware and software ideas. The hardware extensions, so there are a couple of things that we are doing around the sparsity. The sparsity handling there is fundamentally what we are trying to do is in sparse linear algebra, to manipulate the sparse data structures as a dense data structure using index and data, non-zero data, and then bring them in blocks into the local memory and work. So fundamentally, into the main memory, we are not issuing sparse addresses.
Like perfect stuff.
Yeah, but this is not always possible. So there are also other things we are trying to do, fundamentally, if you have to generate sparse data streams, in some application you cannot do this trick, then we are also working on hardware to fundamentally reduce the amount of useless data that you have to move, for example, in these large buses. But this is not described here. But it's called AXIPAC, and it's fundamentally an extension to the AXI protocol to actually reduce, improve the efficiency of the NOC data transfer. But I didn't have time to cover it.
Okay, so let's thank you, Luca. Thank you very much.